Hello, everyone, and welcome to this deep dive into the fascinating world of artificial intelligence. Today, we are going to explore the machine learning landscape. If you're just starting out, the field of AI and machine learning can feel a bit like a vast, unexplored wilderness. There are dense forests of mathematics, high peaks of complex algorithms, and rivers of flowing data. It can be overwhelming, but don't worry. Think of this presentation as your explorer's field guide. Our goal today is not to get lost in the weeds of complex code, but to understand the lay of the land. We want to understand the high level concepts, the maps, and the compasses that data scientists use to navigate the terrain. By the end of this video, you will have a solid mental map of how machine learning systems work, how they are classified, and the common pitfalls to avoid on your journey. Let's start by grounding ourselves in reality. A common misconception is that machine learning, or ML, is just futuristic science fiction, something involving sentient robots or flying cars. But the truth is, machine learning has already moved from the realm of fantasy into your pocket. It's a utility used by billions of people every single day, often without them even realizing it. Well, the mathematical roots go back decades. Think of early optical character recognition that could read numbers on checks. The first major mainstream breakthrough was actually the humble spam filters in the 1990s. It learned to flag junk mail so well that it became invisible to us. We just took it for granted. Since then, a massive wave of applications has followed. Whether it's a voice prompts on your phone, automatic translation of websites, or product recommendation on Amazon. ML is the engine quietly powering these features. And now, with the explosion of generative AI like ChatGPT and Gemini, AI isn't just the background anymore. It has become the service itself. So, how do we define a compass? What does it actually mean for machine to learn? It's easy to anthropomorphize computers, but we need a scientific definition. At its core, machine learning is the science and arguably the art of computing programming computers so they can learn from the data. Let's look at two classic definitions. Arthur Samuel, a pioneer in the field back in 1959, described it as giving computers the ability to learn without being explicitly programmed. That means not writing a specific rule for every single scenario. Later, Tom Mitchell provided a more engineering-focused definition, which acts as a compass. He described it as a triangle of task, experience, and performance. Consider a spam filter. The task T is to flag spam. The experience E is the training data, the examples of spam and non-spam emails you feed it. And the performance P is the accuracy, the ratio of correctly classified emails. The key takeaway here is that simply downloading a copy of Wikipedia to a hard drive isn't learning. Learning only happens when the system performance on a task improves after gaining experience. Why should we bother charting this new territory? Why not just stick to the traditional programming? Well, let's look at the traditional approach versus the machine learning approach. In traditional programming, if you wanted to build a spam filter, you would manually study all the emails. You notice that spam often contains words like number 4, you, or free. You would then write explicit code. If subject contains for you, mark as spam. You test it, find it fails on new tricks, and then write some more rules. Eventually, you end up with a tangled mess of complexity that's very hard to maintain. Now, look at the machine learning approach. You don't write the rules, you provide the data. The algorithm automatically learns the patterns, detecting frequent words or strange sender addresses. The resulting program is shorter, easier to maintain, and usually more accurate. But the real superpower here is adaptability. If spammers change their strategy and start using the word for instead of for, that number four, and start writing it as for you instead of for you, a traditional program breaks until you go ahead and manually update it. An ML system, however, notices this new pattern in user flagged emails and adapts automatically without you lifting a finger. Now that we understand the why, let's take a glimpse at the terrain. The world of ML application is incredibly vast, and different tools are used for different environments. We have image analysis, where convolutional neural networks, CNNs, and transformers are used to classify products on a factory line or even detect tumors on brain scans. Then there is a natural language processing, or NLP. This powers everything from summarizing long legal documents to the chatbots we talk to daily. In the business world, we rely on forecasting and prediction to estimate company revenue or detect credit card fraud using anomaly detection. We also have data interpretation, which uses clustering to segment customers based on purchasing habits, helping marketeers target specific group. And finally, the frontier of autonomous system, where reinforcement learning helps agents like AlphaGo learn complex strategies or helps robots learn to walk. Each of these icons represent a massive subfield, but they all share the same underlying DNA, learning from data. To navigate the landscape effectively, we need a system of classification. We can't just lump all ML systems together. In this guide, we use three key criteria to categorize any machine learning system. Think of these as three different axes on our compass. First, we look at training supervision. How is the system guided during training? Does it have a teacher correcting it, or does it learn on its own? Second, we look at learning cadence. Can the system learn incrementally on the fly, or does it need to be trained all at once? This is the difference between online and batch learning. And third, we look at the generalization strategy. How does it make predictions on new data? Does it compare new data to old examples, or does it build a mathematical model? As you can see in the examples at the bottom, these categories are not mutually exclusive. A state-of-the-art spam filter, for instance, can be described as online, model-based, supervised learning system. Well, let's break these down one by one. We enter region 1, the well-mapped lands of supervised learning. This is the most common type of machine learning used in industry today. In supervised learning, the training data fed to the algorithm includes the desired solutions, which we call as labels. The system effectively learns from a teacher who says, this image is a cat or this email is a spam. There are two main tasks here. The first is classification, where the goal is to predict a category. As shown in this diagram, the model takes emails and separates them into a spam or ham. The second task is regression. This is used when you predict a specific numeric value. For example, predicting the price of a used car. You feed the model features like mileage, age, and brand, and the target label is the price. The model finds the numerical or mathematical relationship, represented here by that line cutting through the data points, to predict the value. Remember these terms. Features are the inputs data and labels are the desired output. Next, we move into the uncharted territories of the unsupervised learning. Here the rule change completely. The training data is unlabeled. The system tries to learn without a teacher. It's effectively wandering through the data, looking for patterns and hidden structure on its own. We take several key tasks here. Clustering is about detecting groups, for example, analyzing blog visitors and realizing they naturally fall into a segment like teen comic fans or adult sci fi readers without being told those categories actually exist. Then we have visualization and dimensionality detection, which takes complex high dimensional data and squashes it down into a 2D or 3D plots so human can understand it. Anomaly detection is another critical use case. The system learns that what normal really looks like, so it can flag unusual instances such as credit card fraud or defective manufacturing parts. Finally, association rule learning discovers relationships, like the famous example of a supermarket discovering what people buy barbecue sauce also tend to buy steak. Between the land of supervised and unsupervised learning, there is a bridge: semi supervised and self supervised learning. Semi supervised learning is incredibly practical because labeling data is expensive and time consuming. This approach is used when you have plenty of unlabeled data, but only a tiny amount of labeled data. The great example is Google Photos. You upload thousands of photos. The system uses unsupervised learning to cluster faces together. Then you provide just one label. You name one person, Jane Doe. The system then propagates that label to the whole cluster. Self-supervised learning is the magic behind modern large language models. Here the system creates its own labels from the data. For example, in image repair, you mask a part of the image and ask the model to predict the missing piece. The original image is the label. This allows for pre-training on massive datasets, creating a model that understands the world, which can then be fine-tuned for a specific task. Now, we reach the dynamic frontier of reinforcement learning, or RL. This is a very different beast compared to the others. In RL, we don't have a dataset of fixed answers. Instead, we have an agent, like a robot or a software bot, that exists inside the environment. The agent observes the state of the world, performs an action, and receives a reward or a penalty in return. It's essentially learning by trial and error, similar to how you might train a dog with treats. The goal of the agent is to learn a specific strategy called a policy to maximize its rewards over time. The most iconic example of this is DeepMind's AlphaGo. It analyzed millions of games and then played against itself millions of times. It wasn't learning during the championship match, it was executing the policy it had already learned. This method is incredibly powerful for robotics and complex game playing. Let's adjust our compass to look at the second criterion: learning cadence. This distinguishes how the system handles the flow of time and data. First, we have a batch learning, also known as offline learning. Imagine constructing a massive dam. You do it all at once. The system is trained using all available data, which takes time and computing power. Once trained, it is launched into the production and it stays static. It doesn't learn anymore. The problem here is model rot, or as the world changes, the model becomes outdated and you have to build the whole dam from scratch. Contrast this with the online learning or incremental learning. This is like adding small stone to change a reverse course. You feed data instance sequentially or in many batches. It's fast and cheap. This is perfect for stock markets or system where data is too huge to fit in memory. However, you have to be careful of catastrophic forgetting, where new data makes the model forget what it learned yesterday, or bad data quickly corrupting the system. A third criterion was classification is the generalization strategy. How does the model handle something it has never seen before? We have two main approaches. First, instance-based learning. This is arguably the simpler approach. The system learns the training examples by heart. When a new instance arrives, it compares to the learned examples using a similarity measure. In the diagram, the new green circle is classified as a triangle because the majority of its nearest neighbors are triangles. This is effective but doesn't scale well. The second approach is model-based learning. Here, the system acts like a scientist. It looks at the examples and detects a pattern, a formula that represents the data. It builds a model. During training, it tunes the parameters of this model to fit the data best. Once the model is trained, you can throw away the original data points and just use the formula to make prediction. This is generally more scalable and how most modern deep learning works. Let's go on a model based expedition to see exactly how this works in practice. Our case study: does money make people happier? We want to see the relationship between GDP per capita and life satisfaction. Step 1 is to study the data. We look at a table of countries like Turkey, the US, and the Denmark. We plot these on a graph. Step 2 is to select a model. Looking at the scatter plot, the data seems to go up in a straight line, so we choose a linear regression model. This model has a math equation. Life satisfaction equals theta plus theta 1 times GDP. Step 3 is to train the model. The learning algorithm searches for the best parameters, theta 0 and theta 1, that minimizes the error, drawing a line that fits best. In our example, it finds that the specific numbers. Finally, step 4 is the inference. We want to predict life satisfaction for a new country, Puerto Rico. We plug its GDP into the train formula and it outputs a predicted life satisfaction, roughly 6. So let's pull back and look at the complete map of machine learning continent we have just sketched out. This visual summarizes everything we have discussed. In the center, we have our machine learning systems. Branching upwards, we categorize them by training supervision, moving from supervised with labels to unsupervised, no labels. With semi-supervised and reinforcement learning branches off to the left, we categorize by learning cadence, the static heavy batch learning versus the dynamic flowing online learning. And to the right, we categorize by generalization, the memorization of instance-based learning versus the formula creating model-based learning. Remember, these aren't separate islands. Any given system is a combination of these traits. You have an unsupervised batch model-based system or a supervised online instance-based system. Knowing where your project fits on this map is the first step to success. However, the trail is not without its dangers. We must discuss the perils and pitfalls. Hazard number one is deficiencies in your raw data. There's a golden rule in data science: garbage in, garbage out. Your model is only as good as the data you feed it. First, you might have an insufficient quantity of data. While humans can learn to recognize a car from a few pictures, machine learning algorithms often need thousands or millions of examples. The Microsoft paper famously noted, sometimes having more data is more effective than having a cleverer algorithm. Second, you might have a non-representative data. This leads to a sampling bias. Third, you have poor quality data, full of errors and outliers. And finally, irrelevant features. If you try to predict a car's price based on the color of the paint, you're going to have a bad time. Feature engineering or selecting the right inputs is very critical. Hazard number two is the danger of overfitting. This is a very common trap for beginners. Imagine you visit a foreign country and the first taxi driver you meet rips you off. You might conclude all taxi drivers in this country are thieves. You are overgeneralizing. In machine learning, overfitting happens when the model is too complex relative to the amount and noisiness of the training data. Look at the graph on the right. The blue line is the true underlying signal. The squiggly red line is the overfitted model. It is trying so hard to fit every single dot, every piece of noise, that it loses the big picture. It performs perfectly on the training data, but it will fail miserably on new, unseen instances because it has memorized the noise rather than learning the trend. For example, a complex model might find a coincidental pattern that all countries with a W in their name have high life satisfaction. It's a fluke, not a rule. So, how do we fix overfitting? We need a course correction mechanism called regularization. Regularization is the process of constraining a model to make it simpler and reduce the risk of overfitting. If overfitting is like trying to memorize every word in a textbook, regularization is like forcing yourself to summarize the chapters in bullet points. You lose some detail, but you grasp the main concept better. In the graph, the red dashed line was our crazy overfitted model. The green dashed line is the regularized model. It doesn't hit every point perfectly, but it captures the general trend much better. We control this by using a hyperparameter. This is a setting we choose before training begins. It acts like a knob. Turn it up and model becomes more rigid and complex, simple. Turn it down and the model has more freedom to fit the data. By forcing the model parameters to stay small, we prevent it from obsessing over the noise. On the other side of the spectrum lies hazard number three, the pitfalls of over and underfitting. This is the opposite of overfitting. It occurs when a model is too simple to learn the underlying structure of the data. Think of trying to wear a shoe that is three times sizes too small. It just doesn't fit the reality. In the graph, we see that data that clearly curves like a U shape, but the underfitting model is just a straight line. It has no hope of capturing that curve. The predictions are inaccurate on the training data and the new data. The reality is simply more complex than the model can handle. The solutions here are straightforward. First, select a more powerful model, maybe a polynomial model instead of a linear one. Second, feed better features to the algorithm, feature engineering. Or third, reduce the constraints. If you have turned the regularization knob too high, you need to turn it back down to let the model breathe and learn. Now that we have built a model, we need to talk about final preparations, testing and validation. How do you know how well a model will perform in the real world before you launch it? Hoping for the best is not a strategy. The only way to know is to test it. We typically split our full dataset into two parts. The first part, usually about 80%, is the training set. We use this to teach the model. The second part, the remaining 20%, is the test set. We hide this from the model during training. Once the model is trained, we evaluate on the test set to get an estimate of the generalization error. This is the error rate on new cases. Here is the key insight. If your training error is low, well, the model thinks it's going great, but your generalization error on the test set is high, your model is overfitting. It memorized the training set but failed the test. But wait, there's a nuance here. We need to calibrate our instruments carefully. There's a trap. Suppose you want to choose between a linear model and a polynomial model, or you want to tune that regularization hyperparameter. If you train 100 different models and evaluate them all on the test set and then pick the best one, you have a problem. You have adapted your model to the test set. The test set is no longer unseen data. You have effectively peeked at the answers. To solve this, we need a validation set, sometimes called as a dev set. As shown in this workflow, we split the training data to create a smaller validation set. We train multiple models on the reduced training set and compare them on the validation set, and we pick the winner. Then, and only then, do we run a final evaluation on the test set to get a true estimate of performance. This prevents us from overfitting to our testing data. Sometimes the terrain is tricky and we have to navigate data mismatch. This happens when the data you can easily get for training is not perfectly representative of the data you'll see in production. A classic example is building a flower recognition app. You can scrape millions of high quality flower photographs from the web, but your users are going to be uploading blurry, dark photographs taken on their phones. If you train on web images, your model might fail on the phone images. If your model performs poorly on the validation set, you don't know why. Is it overfitting? Or is it because the web images are just different from the phone images? The solution is to hold out a piece of the training data in the train dev set. If the model works well on the training data, but fails on the training dev set, it's overfitting. If it works on the train dev set, which are the web images, but fails on the validation set, phone images, then you have a data mismatch problem and you need to simulate phone imperfection in your training data. Well, we conclude our exploration with the explorer's first principle, the no free lunch theorem. This was proposed by David Woppert in 1996. It states that if you make absolutely no assumption about the data, there is no reason to prefer one model over the other. A complex neural network is not guaranteed to be better than a simple linear regression for every single problem. A model, by definition, is a simplified representation of reality. By choosing a model type, you are making assumptions. For example, by choosing a linear model, you assume the data follows a straight line. The no free lunch theorem reminds us that there is no single best map for all territories. You must make reasonable assumptions about your data to narrow down the list of models, and then the only way to know for sure which is the best is to evaluate them. You have to test the terrain yourself. So, here we are at the end of our field guide. Let's look at the Explorer's field notes for a summary of what we have learned. ML's goal is to make sure or make machines get better at a task by learning from data rather than being explicitly programmed with rigid rules. We saw that we live in a diverse world where systems are categorized by their supervision, supervised versus unsupervised, their cadence, which are batch versus online, and how they generalize, instance versus model based. We walked through the typical project lifecycle, gathering data, training on algorithm, tuning parameters, and performing inference. We identified the key to success, avoiding the perils of bad data, whether it's too little, non-representative, or noisy, and avoiding bad models that either underfit or overfit the reality. And finally, the final check. Rigorous evaluation using validation and test set is not optional. It's the only way to ensure your model is ready for the real world. Thank you for joining me on this expedition through the machine learning landscape. Happy exploring. Please do subscribe the channel for more videos of this kind. Thank you.